hello everyone. I hope you are all doing well. I am Katerina Valta, and along with my colleague Eleni Zioni, we would like to welcome you to the 6th webinar that it is produced in the framework of the Horizon 2020 CUTLER project. Our webinar is related to the modeling of environmental impacts of urban development decisions with the use of big data. So before starting, just some few housekeeping notes. As you know, the webinar is live streamed on Facebook. The webinar will be also recorded, and the recorded information will be shared at the project's YouTube channel and our Facebook page. We will also provide you with our presentation. This will be shared on the CUTLER website. I would like to kindly ask you to mute your microphones during the presentation and also switch off your cameras if this is possible. At the end of the session, we will have questions and answer session, and then you can raise your questions, and even better, you can send it on the chat, and we will take care at the end. So what is in our agenda? First of all, we will start with a small introduction of the presenters and of the CUTLER project, including the pilots. Then we will see the overall methodology that we developed in the CUTLER project to assess the environmental impacts with the use of big data. Then we will focus on the needs for modeling the environmental impacts, as well as on the selection of the framework to frame the indicators that we have used in the assessment. And finally, we will close this part with the main takeaways up to this point. Then my colleague Eleni will follow on the third part, in which you will learn more about the IT support mechanisms. In particular, during this part, you will learn about the types of data, visualizations that we have used, and which can be used in order to support policy evidence. Then we will share with you some dashboards that we have prepared, and of course we will close the presentation with the important takeaways from this part as well. And finally, we will have the question and answer session. So once again, welcome everybody. I am Katerina Valta, and along with my colleague Eleni Zioni from Draxis Environmental, we are happy to be your presenters to our topic today. I am a chemical engineer with a PhD and a Master of Science in Environmental Engineering. I have joined Draxis in 2017, and my expertise lies in environmental management and environmental impact assessment. Then, Eleni, would you like to introduce yourself, please?
Yes, thank you, Katerina. Welcome, everybody. My name is Eleni. I am an electrical and computer engineer. My specialization is in electronics and computer science, and I joined Draxis Environmental in 2018. Well, for the past 2 years, I have been working on planning, organizing, and coordinating with dev teams to execute specific IT goals in relation to software development. I'm happy to be here today.
Thank you, Eleni, for the introduction. Now, among other roles in the CUTLER project, Draxis is leading the work package related to big data analytics for assessing the environmental impact. Just a few comments for our company. Draxis Environmental is an SME located in Greece and is committed in providing custom-made state-of-the-art software solutions, as well as scientific consulting services in the fields of air pollution, water management, waste management, and general on environmental challenges and e-governance. Let's start with a brief overview of what the project is about, what the CUTLER project is about. CUTLER's main objective is to shift the existing paradigm of policy making, which is largely based on intuition, towards an evidence-based approach, which will be enabled by big data. In particular, focusing on 5 cities with waterfront areas, we exploit the wealth of the data that are generated in these cities in order to help the policymakers through the development of an innovative platform that will utilize all this data to make assessment for their decisions. Today's webinar is related to the use of big data, in particular for defining the environmental impacts. As already mentioned, the proposed solution is implemented and tested in 5 pilots. So we start with the first pilot. This is the pilot of Thessaloniki in Greece. In this pilot, public authorities in the municipality use the CUTLER platform to optimize, monitor, and evaluate a new control parking system at the waterfront area facing Thermaikos Bay. Our second pilot is related to the municipality of Antalya in Turkey, which uses the CUTLER platform as a decision-making tool that will allow to design, monitor, and assess policies for increasing the visitor numbers and protecting the natural habitat in the Duten waterfall area that you can see here in the picture. Then we have our third pilot. This is the pilot of Antwerp in Belgium, which uses the CUTLER platform as a monitoring tool that allows to visualize all water-related area and also to prioritize actions described in its urban water plan strategic plan. Then the fourth pilot is the Core County pilot in Ireland. This is in this case, the Core County Council utilized the CUTLER platform to make more evidence-based decisions on future access mechanism to the Fort Meagher. And finally, we have our fifth pilot. This is the pilot of Vicenza in Italy, which uses the CUTLER platform to support authorities in making informed decisions with regard to the development of flood risk reduction measures through structural interventions. Now we move on to the second part of assessing the environmental impacts. Assessing the environmental impacts of projects, plans, policies, products, or processes has been in focus for many years, for the last 50 years globally at least. It was in 1969 in USA that the National Environmental Policy Act was first adopted, which means that the environmental impact assessment went into the into legislation. NEPA required the agencies to assess the potential environmental impacts of their proposed actions and to consider reasonable alternatives to those actions. Then in 1985, we can see the trend of environmental impact assessment coming to the EU legislation with the Environmental Impact Directive, in which it was requested for certain public and private projects to implement an environmental impact assessment in advance. This was followed by 2001, when again in the EU legislation we have the strategic environmental assessment need, which was mainly focused on the impact assessment of certain plans and programs. Based on the above, it has become clear that the process of assessing the environmental impacts of projects, plans, programs, policies, or processes can be considered in two different stages. First, we have the pre-decision stage, which practically provides with a helpful process, let's say, in order to identify in advance potential impact that such a policy can have, or at the post-decision stage, which is after the decision has been taken for monitoring and auditing of decisions that have already been made. So as you can already feel, the target to be achieved involves the active collaboration of different stakeholders. Based on our experience from the CUTLER project, the most important include, first of all, the public authorities, as you can see here with the yellow color, the environmental experts, of course, the data analysts and developers. In the context of the CUTLER project, the above-mentioned stakeholders have been collaborative extensively, but I'm sure that you will be wondering which is the best way to collaborate between those many stakeholders. So, based on our experience from the CUTLER project that now runs almost for 3 years, in this slide we summarize what we propose as the best approach to involve those partners. So, in both cases of pre-decision and post-decision assessment, the first step is the definition of the project or the measure, let's say, under investigation from the public perspective, let's say. So this is important to be defined by the public authorities. Then Analysis of the decision and identification of impact categories shall initiate, and this should be done by the environmental expert just after the definition of measure has been done by the public authority. Then, once the basic policy analysis is conducted, a parallel work to identify relevant environmental data takes place. This step is led by the environmental expert in collaboration with the data analyst, as well as with the public authority, because there are many cases that the public authorities owns such data. In parallel, modeling of environmental impact is initiated, and this is done by the environmental expert. In addition to that, and once the basic environmental data are identified, a very important step is to define the framework to frame the indicators that you will do the assessment, if you choose, of course, the indicator-based assessment. This is done, of course, by the environmental expert. Then, when more or less all the above mentioned steps have been formulated, the development of the crawlers to collect the data must start, which will be led by the developers in collaboration with the data analysts. Which finally bring us to the next step, which is the development of the environmental widgets, which show and depict the environmental data and indicators. This is led by the developer in collaboration with the environmental experts. Finally, after a period of internal and external testing, the policymaker can use the widgets to assess the environmental impact of their policy. So in the framework of the CUTLER project, our work in Draxis was mainly focused on this gray box. In my presentation, I would like to step into two of these steps. This is the modeling and also the selection of indicators to frame the assessment. Then my colleague Eleni will also come back to the other steps as well. So as I just said, I will first focus on the step of modeling. Modeling of environmental impact is a demanding exercise, as it often requests for specific expertise in the environmental modeling domains. I mean, there's sometimes need to model data that are related to the quality of air, either or water or for soil protection. An example of the modeling needs in the framework of the CUTLER project was the modeling of the air quality index. This index reveals how clean or unhealthy is the air and what associated health effects might be a concern. The AQI, the lower the level of air pollution and the lower the health concern. Now, AQI can be calculated based on the equation that is provided in this slide. This is provided by the Environmental Protection Agency in 2006. And in this case, the concentration from air quality monitoring stations can be used as real-time data to calculate this air quality index. This is done in collaboration with the breakpoints that are provided by the Environmental Protection Agency. And finally, we have the calculation of AQI based on various ranges in this value. And as you can see here, it is depicted with different colors for each category, its quality in the quality of air, let's say. For example, we have the green for the good, the moderate, which is yellow, the unhealthy for sensitive group, which is orange, and so on and so forth. You can see the other categories. Another example that we faced in CUTLER was the modeling of the water runoff to assess the garden street as a climate adaptation measure against flooding using rainfall and water flow real-time data. This was done in collaboration with Ronnie van Loeveren from the Environmental Department of the City of Antwerp. Here we combine the rational method and the linear reservoir model. In the first place, we use the rational method in order to calculate the runoff based on real-time values that are provided by the rainfall intensity, as you can see here with I. And then we combine this with the linear reservoir model in order to calculate the routed runoff. And you can see here the equation that was used. And in this diagram, you can also see the calculated runoff, and which is then compared with the one that it was measured through the use of sensors, which is the one with the green. Then we move on to other examples that we also used modeling. As for example, we have the modeling of nitrogen oxide emissions using equations of the Coppert model. Here we use the real-time vehicle speed data for some specific routes at Thessaloniki case. We also faced some modeling, let's say, challenges in order to model emissions from alternative sources, but in this case with static data. As for example, we have the modeling of nitrogen oxide, carbon monoxide, and particulate matter emissions for let's say, alternative transport routes and mechanisms, and also the modeling of carbon dioxide from energy consumption. I will now move on to the second topic that I would like to discuss here today, which is the actual assessment through the use of indicators. In our case, we use the indicators in order to assess the impact in the environment. Some theory behind the indicators. Their difference, we have different frameworks for the indicators, and the different lies between what they are focusing on. For example, we have the pressure state response framework for the environmental indicators. We also have the driving force state response framework, the driving force pressure state impact response framework, and finally the theme and sub-theme framework for indicators of sustainable development. In our case, we have used the theme-sub-theme framework. This is a widely used framework. Such framework reflects a hierarchical approach where issues and sub-issues, let's say, are considered, and they finally end up to specific indicators. Such frameworks are the theme sub-theme, let's say, framework is very easy to use, and that is why it's very flexible, and that is why it has become popular. In our case, in the case of CUTLER, our framework started with 3 topics. These are the climate, environment, and resource. Then we moved on with the 4 themes, including climate issues, water management and quality issues, air quality and resource efficiency. And then we subdivided further to sub-themes, including climate mitigation, climate adaptation, water management, water quality, air quality in district scale and in local scale, and energy and raw material depletion. All these ended up to 31 indicators. I would like to say here that this approach was based on a methodology that it was presented on another very interesting Horizon 2020 project, the Nature Facilities project. In this slide, you can see the overall depiction of the environmental indicators that were selected and the topics, themes, and sub-themes. Of course, it's not readable in this slide, but I would like to share with you deliverable 5.3, in which we include all the information in this area. Then for each of the indicators, we have developed a fact sheet. In this slide, you can see the fact sheet components, starting with the indicator name. Then we move on with its description, its calculation method, and the categorization that it belongs based on the themes topics discussed earlier. We also included the measurement unit, the pilot and data that are relevant to it, its interpretation, and its connection with the sustainability issues. In this slide, you can see an example of a completed indicator fact sheet. which includes all the information just mentioned before. Of course, there are fact sheets for all the indicators and are included in deliverable 5.3 that I just mentioned. Now, closing this part of the presentation, I would like to summarize some of the challenges and main takeaways up to this point. First of all, I would like to say that in order to start the assessment of the environmental impacts, it is very important to have the decision to be assessed clearly defined. So in case that when starting doing this, you feel that this is not clear, you have to go back to discuss it with the policy, with the public authorities. And you should also have in mind that this should be considered during the design of your process. Then, what was also challenging is the identification, prediction, and evaluation of the different impacts. And this is because it's not on a one-cut solution which is applicable to all decisions, but on the contrary, this identification of impact and assessment is always pilot-specific and depends on the decision to be assessed, but also on the data availability, and it needs customization in terms of impact forecasting. Then, as we saw, the indicators that are organized by the appropriate framework can be used for supporting public authorities to the environmental impact assessment. It's an easy way and it's very, let's say, end-user friendly. And also the use of the sub-themes framework can be applicable, is easy to use, and can be adapted to the various needs in the decision-making process of the public authorities. Closing this first part, I would like to mention the great importance that the data and data availability and quality has, but more insights on this will be given by my colleague Eleni. That being said, I would like to thank you from my side, and Eleni, the floor is yours.
Thank you, Katerina. Well, hello again, everybody. The next part of the webinar will focus on the use of technology to support the assessment of policy impacts. I'd like first to come back to the important steps that Katerina had previously presented to you. I would like to focus my presentation on the following three. First of all, the identification of relevant environmental data. Then we will talk about the development of the crawlers to collect the data. And finally, the development of the environmental widgets to display the data to the public authorities. In the next slide, we will present our methodology and more specifically, the information flow. It comprises of 4 independent blocks, data sources, crawlers, Elasticsearch, and Kibana. The data sources block contains all the information defined from the 5 pilot cases. The data sources can be either content on websites, existing databases, services providing content through APIs, or files provided by the users. In order to get the data from the sources, we have created several crawlers. A custom crawler was created specifically for each one of the data sources. We have developed crawlers using Python and Node.js, and all the software is stored in GitHub. Apache Kafka was used in the project, and that was done to provide reliable real-time streaming data pipelines. And for that reason, all the crawlers comprise of a producer and a consumer. The producer basically publishes the data to Kafka, and the consumer subscribes to a certain topic and processes the data there. Finally, we set up Supervisor. This is a process manager. It handles the consumers for the cases where the crawlers are updated frequently. We used Elasticsearch to store the data, and the data is organized in indexes. The indexes follow a specific structure, and they also provide the mapping that Kibana uses in order to create the visualizations. You can see here an overview of the indexes that were created for each one of the 5 pilots in the CUTLER project. Kibana is an open source data visualization plugin for Elasticsearch. It provides visualization capabilities on top of the context that is indexed in Elasticsearch. What we developed is a custom collection of graphical elements. They are charts, tables, maps, anything you can think of, and they were combined into groups, forming multiple dashboards. Here also is an overview of the dashboards that were created per pilot. On the first block, we identified and collected many different environmental data sources. Each type of source, you can see them all listed here, may be associated with one or more pilots. And when we have the information in more than one pilot, the exact content of the data and the format of the data may vary from case to case. So we approached each case differently. For example, first off, we have historical weather information. This type of source has many different origins since it applies on many pilots. And we worked with Excel files provided by users that contained information measured by sensors. We also worked with refined Copernicus data that were retrieved through an API, and also sensor measurements that were provided directly through an API. For 4 of the pilot cases, a weather forecast was provided. This is a forecast for the next 7 days, and it is basically a service accessed through an API. This is one of the cases where the data is updated every day. In 2 cases, it was important to measure the water level. The first one was in the case of Antwerp. It includes water level in groundwater. This has both historical values provided in Excel files and also real-time values by sensors. And it also includes real-time data about water level in open water and sewers. The second case was the Cork pilot. This is about water level in the coastal areas. And we have both historical data and real-time data that are gathered by sensor, and they are provided as a service through an API with frequent updates. Water quality information was used in many pilots, and we have identified that in all cases, the sensor measurements were provided in Excel files because lab analysis was required and we couldn't get the values real time. A large network of hydrometeorological sensors that is located in the area of Vicenza provided historical values in Excel files and also real-time data by sensors that are sent through an API weekly. For the Thessaloniki pilot, it was important to calculate the emissions from vehicles, and for that we used measurements of vehicle speed on certain routes around the city, which were parsed from a web page. Energy consumption information that was related to water pump operation to create more water flow was provided in an Excel file, and it was used for further modeling. The air pollutants concentration was indeed a very common data source among the pilots. It had many origins as well. We mostly worked with Excel files containing historical sensor measurements and also near real-time measurements through an API. This is the data that is used to also calculate the air quality index. Then we also had many GIS data. The first data source is about environmentally protected areas. This is included in one pilot, and they are retrieved using Web Map service or by inserting shape files manually into Elasticsearch. Additionally, we had GIS data that is used to describe the territory in the Vicenza area and also to provide the Corinne land cover map. This is also by using shape files. And the last 2 data sources are also provided via shape files, and it's about flood hazard and risk maps that are used in 2 pilots, and also the result of a flood forecast model that is provided by the users. Now, for each one of these data sources, it was important to create a customized crawler based on its needs. During the development of the crawler, we focus on 3 aspects. The first one is quality control. We check if the data is complete and if there are duplicates. Then we move on to harmonization. This is a multi-step process. Enrichment of the data set is important to provide information that is needed in Elastic and Kibana. For example, station geolocation is a very good point because in most data sets, it is represented with 2 variables, lat and lon, but this is not an acceptable format for Kibana if we want to show it on a map. Also, we had to rename some parameters to match the environmental data model protocol. For example, sometimes the data contain measurements at different units for the same parameters. Also, data enrichment was the next step. Sometimes an Excel with not contain units of measure or the location of the station. So we had to provide that. And we also need to represent some values with a Latin character set. For example, we had some fields in Greek. Data aggregations were required in some cases in order to be in line with the visualization requirements in Kibana. That entails grouping of parameters and maybe changing certain data types and formats. Also, it was important to harmonize geographical and daytime information. This basically means to use the same spatial reference system and to refer to the same time zone. For that, we were using UTC. In some cases, further calculations were required to produce more complex parameters. This means, for example, the calculation of the air quality index or the emissions calculations. And this concludes more or less the development phase of the crawlers. After it was developed, then it is ready to be used. A typical process is the one you can see here, where first of all, we start the producer of the crawler. As I said, there is a producer and a consumer because we use Apache Kafka. The producer gathers the data from the source, or it opens the Excel files that is stored somewhere. Then we follow the steps that we mentioned before: quality control, harmonization, and calculations. Then it broadcasts the data into the Kafka topic, and the consumer of the crawler is triggered and consumes the data. Then the data is injected into Elasticsearch in the form of JSON documents. You can find all the developed software in the link in GitHub below. And I would also like to say that this is a general process that was used in all cases, but there were some instances where we had to collect data frequently, and for these cases, we set up cron jobs in the production servers of the pilots in order to run the producers on a daily basis. And then we used supervisor, which is the process manager I mentioned before, to keep the consumers running so that they will be triggered and they would consume the data that were broadcasted by the producer. Let's talk a bit about Kibana. Kibana, as I said, is a user interface. It is very well connected with Elasticsearch, and it lets you visualize the data that are indexed in Elasticsearch. The visualization page allows the user to create or modify various visualization modules. You can see that there are many options: bar, lines, pie charts, scatter plots, and you can then combine them into the form of custom dashboards. During our work, it proved very challenging to identify which of these options are better suited to each one of the collected data sources that we mentioned. After much effort and research, we concluded that we should provide 2 overall categories of visualizations. First of all, we have descriptive graphs that contain the display data without further analysis. That is mostly the data as they come from the crawlers, and these visualizations allow the user to reach their own assumptions because they also have expertise on these domains. And we also have visualizations that display the indicators and the assessment of the environmental impact, mostly KPIs. So we had to adjust many times our approach as we proceeded with the development, because as we went, we gained a better understanding of a deeper analysis of the data. And we also faced some limitations by Kibana visualizations. So we had to go back and redesign our approach. And of course, when we got our first user feedback, it was important to incorporate that and change our approach again. So especially due to Kibana restrictions, we proceeded to create 2 plugins to present some of the indicators appropriately. The first Kibana plugin is specifically customized to visualize certain KPIs in the form of a gauge diagram. This is the one that you see on the top. The users can select 2 years from 2 drop-down lists, and they can visualize whether the change from 1 year to the next was positive or negative. To better understand that, I will provide an example. Let's say that you want to measure the concentration of a certain air pollutant that is harmful to the citizens. So you have the values. What this plugin does is to show you that if the concentration has increased, then the needle will be in the negative, in the red zone. But if it was reduced, which is what we are aiming for, it will be on the green zone. And the second Kibana plugin was specifically customized to include layers. It is a map plugin. It includes layers for the area of Cork. The controls of the map are twofold. You can see on the right that there are many layers that you can select. And on the left, there is also a distance measuring tool. The need for this plugin arose while we were using earlier versions of Kibana that did not have appropriate GIS data visualizations. But even though we use the upgraded versions in the second phase of development, we kept this plugin because the distance measuring tool was very important to the users because it allows them to calculate the distance of the location of the implemented measure and other environmentally protected areas. Over the following slides, we will present our results on how different data sources were visualized in Kibana in different ways. First of all, we have the historical weather information. As I said, many pilots had this information, so we had the opportunity to do different things. We have line graphs that show temperature, and we can see that we can include some thresholds like max and mean temperature. We also have an area graph showing the sum of total precipitation for last few years. We have a heat map showing the average wind speed per month. This is important for stakeholders in order to see which months have the greatest wind speed, and this is with regards to a certain harbor area. We also have the average temperature per month. This is used by including data from many years, and we can see the tendency of temperature to get higher during certain months. This will be taken into consideration by the stakeholders for the measure implementation. And there is also a pie chart showing the wind frequency and direction. Even though this information does not relate directly to the impact assessment, the users considered it very, very useful to have this as complementary information so they have a well-rounded view about the measure they are going to implement. The next one is a 7-day weather forecast. This was provided for 4 out of 5 pilots. What we did basically was to show a line diagram for the next 7 days. In this diagram, the user can see information about each and every hour of the next 7 days. And we also have a quick overview, some metrics, providing values for the next day for 4 parameters that we include in the weather forecast. This was about the case of Antwerp. It was important to show the water level in the groundwater, open water, and sewers. and also the volumetric flow rate of runoff, which is used in the modeling that Katerina described before. For this case, as I said, we have many sensors, so it is important to show their location on the map and also provide some line graphs where you can see how the values change over time. And for the graph on the bottom left, this has to do with the values of the runoff, and they provide two values before and after the measure. Water level was measured also in the Cork pilot. Here we have real-time data. They are provided every day. Of course, we saw the location of the map. Here's an example of what the tooltip on the map looks like. We can select any information we want to show on this tooltip. And on the bottom, you can see a line graph where the values of the water level change over time. And this data, as I said, is updated very frequently. About the water quality, this was also a very common data source for the pilots. We have a map. We have many different types of stations, so it was important to show them with different icons so that they are distinguishable to the users. Tables is a very common format. It provides concentrated information. The users always prefer it. And we have two types of line graphs. One line graph is common to the ones you viewed earlier. It provides the changes over time, but we also have a different type of line graph where you can see the concentration of a certain pollutant across different stations. We also have the KPI that we showed you before, the Gates plugin, that shows if the concentration of a certain pollutant has increased or decreased during certain years. This is an example of how the hydrometeorological sensors are depicted. Vicenza has a great network, many different types of sensors, so they are all depicted on a map. It was important for the users to be able to glance quickly at metrics that are important to them. So we provided this window, and the color coding also helps them understand if there is an alert or no. And of course, we provide all the measurements from the sensors in forms of line diagrams. In order to calculate the emissions that are produced by cars, we use the vehicle speed. This is connected to NOx emissions modeling that Katerina described earlier. Again, we have some metrics that are important for the user to consider quickly. We also have a line graph. We can see here how the emission factor and the speed changes over time and what is the connection between them. And this is one of the few cases that we have data with very close intervals. We have very often these types of data, and this is updated also daily. Again, tables for seeing all the information at one place. The Gates plugin that helps you understand what is the change over time, and another type of complementary visualization showing the average monthly speed for all the routes that we have gathered data from. Also, it was important to measure energy consumption information. This relates to the use of pumps in order to keep water flowing in a waterfall area. This relates also to CO2 modeling. What are the emissions produced by this energy consumption? So what we have provided is a heat map showing what are the months with the maximum consumption of electric energy. This helps the stakeholders to focus the measure implementation on certain months that they see that there's heavy consumption. Again, the plugin is very useful here to show the difference between 2 years, for example, before and after the implementation of the measure. And we also have certain metrics that are important for the user to quickly look at. As I said, the air pollutants concentration was very common. We have many stations measuring the pollutants, and they are depicted on a map. We have a line graph showing the difference over time, aggregated monthly values. And this colorful graph here shows the change of the AQI values. You can see that when we have darker colors, that means that the concentration of pollutant is higher, it is more unhealthy for the citizens, and this is where when the implementation of the measure should really focus on. Again, we can see the indicator to check whether the implementation was successful or not, and if the concentration decreased. As I mentioned before, we had some GIS data to visualize. This is the view of the plugin that we have developed. There are several layers about environmentally protected areas. These are some examples. And of course, the user can select the distance measuring tool to check the distance of the location of the measure and the distance from the protected area. This is another example of GIS visualization. This is done using the tools provided in Kibana directly. We have here the information describing the territory around Vicenza. We can include many layers on the map. The user can select or deselect everything he wants to see or not, and then he can visualize them on top of each other on the map. The next one is about the flood hazard and risk maps. In the first case, we have the view from the plugin. This is about the Cork pilot, where they want to implement certain measures, but we can see that there is a possibility that the flood from the coastal area will have a conflict with the measure implemented. So they have to take this into consideration. And in the second case, we have the maps from directly from Kibana tools, where the users can visualize the risk for flooding. And the color coding is also very helpful in this case, as we see that the darker colors are more in risk than the other areas. This is an example of how the flood forecast model is visualized. This is basically shown on a map with different alarm levels, and the rest of the diagrams is the information that was used in order that was used inside the model in order to produce the results that are visualized on the map. It's about elevation in rivers and this kind of information. This is our last type of visualization. It has to do with the KPIs for emissions used to compare the use of a car transport system and a boat transport system. This has to do also with the emissions modeling. In the first graph, the user can see all the emissions and compare the emissions between cars and boats, and they also have the option to view the different values side by side in gauge diagrams and compare what would be the most environmentally friendly transport option. All the separate graphs that we have been showing you can combine into groups, basically forming dashboards where all the graphs interact with one another. In the following slides, I will quickly show you an overview of all the dashboards we have developed for the 5 pilot cases. For the pilot of Thessaloniki, we have collected 12 data sources, we have identified 18 indicators, and we have developed 11 dashboards. I will not get into detail about the dashboards. I will just say that we have air quality information, water quality, historical weather, and weather forecast. And we also have the KPIs for comparing the impact of car versus boat use. For the pilot of Antwerp, we have 10 data sources, 2 indicators, and 4 dashboards. These dashboards were produced in collaboration with some other partners as well. This has to do with historical groundwater level and precipitation data. Of course, the real-time measurements from the sensors, there is a great network there. And there is also a final dashboard which helps the user select the optimum location for where to implement the measure. For the pilot of Antalya, we have collected 5 data sources, we have defined 11 indicators, and we have 9 dashboards. The dashboards contain information about air quality, water flow, and the pump operation to keep the water flow running, historical weather information and weather forecasts, and also the information of the energy consumption of the pumps. For the pilot of Cork, we have 16 data sources and 11 indicators, while we developed 7 dashboards. We show environmentally protected areas, the water level monitoring, historical weather information and weather forecasts. And we also have water quality and the comparison between car versus use of boat transport system. And for our last pilot, this is the pilot of Vicenza. We have collected 7 data sources. We have 8 indicators, and we developed 7 dashboards. And the dashboards contain information about the flood forecasting model, the hydrometeorological sensor network, the weather forecast, and then the GIS data about the flood hazards and risk maps, and the complementary information about the area. So before we go to the demonstration to show how all of this works, we would like again to bring up some challenges we faced during the implementation process. Well, identifying the data sources was extremely challenging. The available data were either limited or private, or it was not directly related to the measure or the area in question. This is why it is very important to closely relate the available data with the measure from the start. Another result of that was that making the connection between the available data and the modeling and indicators proved demanding, so that should start as well as early on as possible. We also faced some difficulties during the development of the crawlers for the initial transformation and harmonization, and especially for the crawlers that run automatically every day and perform changes on the fly. And in some cases, we even had to go back after the first implementation and change things in order to compensate for certain Kibana limitations. So this is also an important takeaway. Don't forget to take Kibana visualizations into consideration when designing the crawlers. Well, further down the road, as I mentioned before, also defining the appropriate visualization was an iterative process. Even when the users were involved in the process early on, it proved difficult for them to conceptualize something that they couldn't see. So as a result, what we did was start to create some visualizations in Kibana and then get their feedback and adjust our approach. Finally, Kibana proved to be an appropriate tool for this project. However, its limitations led us to develop plugins to cover some extra needs. But in any case, the newer version provides many options, and they will be sufficient for these types of data and visualizations. Now at this part, we will present to you the interactive environmental dashboards we created. So just let me share my screen. I think that, Filarete, you have to make me presenter. Thank you. Okay, so this is the first example of a dashboard. This has to do with the air quality index that we calculated for the case of Thessaloniki. The first thing when you use a dashboard is to select the correct time period on the top right corner so that you will see data that is related to your aim. Here is a drop-down list where the user can select or deselect monitoring stations. All the graphs in the dashboards are interconnected, and they change automatically when certain filters are applied or selections are made. Here is a heat map. The lines correspond to days, and we can see that each day is colored according to the values of the AQI for that day, and the user can quickly see whether at an area the air tends to be polluted or not. We can see that, for example, for the station in Aptapiriou, the air is cleaner than the station in Egnatia Street. This is a line graph where we can see how the value changes over time. And we also have a map showing the stations that we have selected on the drop-down list, and the color of the station also corresponds to the level of KPI for that station. Here is the plugin that we were discussing. The user can select the 2 years. Well, this is affected by the time filter, so if we had a bigger range in the time filter, we could select more years here. But this value here means that the AQI was a bit worse in 2016 rather than 2015. And we also have this graph here where the user can quickly see how the AQI changes over time and which days the air is more polluted. Another example is this dashboard here. This is the one about the KPIs comparing the levels of emission from cars and boats for selected years. What the user can do is we have an estimation for the next 10 years. So the user can select which years they want to compare. They should select 2 years. So let's say, for example, that I select 1 and 5. They can also select a scenario, a rather pessimistic scenario containing, fewer visitors coming, or a main scenario, or an optimistic with more visitors coming. Let's say I select this one, and they can see all the emissions, or they select a certain emission they want to focus on. So now here they can comparatively see the emissions from cars and boats. We can see that in general, the emissions from cars are much higher, but they can also see the specific values compared by year and by emission in these gauge graphs. The dashboard is color-coded, so everything green relates to cars and everything blue relates to boats, so the user can go over it more easily. Another example is, for the case of Antalya, a dashboard about the water pollutants in the river and the pump operation to keep the water flow high. Here they can also select a certain parameter they want to monitor. These are about pollutants in the water. They can see the change of values over time. The tooltip provides all the necessary information, and this is about a monthly aggregation. They can easily deselect the filters, and as I said, all the graphs are interconnected. So for example, if I select a certain month here, I will see values only for that month. Here we can see, for example, for the month of April, what is the water flow before and after the pump operated, so they can see if the measure was successful or not. We basically measure the water flow before and after the pump, and we see that yes, the flow increased, so that that was successful. There is also information about the CO2 emissions from the pump operation. The more kilowatts per hour are consumed, then the bigger the CO2 emissions from the pump operation. And again, concentrated information for the energy consumption attributed to different fuel types. We have made the research based on oil, natural gas, coal, and these are the fuel types. Another example is the dashboard about the energy consumption. We can see the energy consumption with time. Again, this is a typical line graph. We have the maximum electric energy consumed per month. So we can see here that, for example, May and August are are months where the consumption is really high and something should be done about these cases. As I said, if I select a month, let's say I select April, all the dashboard provides information only about this month, so it is very interactive and easy to use. This is information that the users wanted to see at a glance. And we also have the KPIs. I can also deselect the filters from here. We also have the KPIs that have to do with the energy consumption. We can see that the energy consumption was better for the second year of operation. And we also have some water quality parameters and a KPI for that. So let's show some examples about GIS data. So this is a dashboard where we have included the plugin that we created. You can see all the layers here. We have selected several implementation measures where what the stakeholders want to build in the area. And this is a layer showing the probability of flood, but there are also other layers, for example, landscape character that you can see as you zoom out is affecting all the area. And there is also a map showing the improvements that the stakeholders want to make around the fort. And a final dashboard that has to do with the hazard and flood risk maps for the case of Vicenza. These are some maps that were created from the hazard and flood risk maps. We can see that it is interactive, and for all the polygons included in here, we have also a tooltip that shows the intensity of the hazard. So the darker the color, the bigger the intensity of the event. And we also have the risk, if it is moderate or high risk, the value changes and the color are according to this legend here. So we can see which areas are in greater risk of flooding, and they should be the focus of the measure implementation. So these were some examples of the dashboards that we have created and how they work, how the graphs interact with each other. Katarina, would you like to just share your screen so we can go to our final comments?
Can you give me your the presenter view?
Okay, let me. I think that.
Yes, it's fine.
Okay.
Can you see my screen now?
Yes, thank you. So to sum up, well, all this information presented to you is included in the 3 deliverables that we prepared during the course of the CUTLER project. The first one includes the methodologies and the initial frameworks for assessing the environmental impact. The second deliverable contains the description of the implementation of the dashboards. And the third one delivers the optimized version and the updated frameworks and, of course, the updated dashboards. You can find all of them at the link at the top. So this concludes our presentation. Thank you very much for your attention, and we are available for questions.
Thank you, Eleni. Thank you, everybody, from my side as well. So we would be happy to discuss any further details or questions that you might have. You can have a look at the chat if it's something. For the moment, we don't have any question. Maybe it's everything very clear to you.
Or maybe it was too much information, I don't know.
So, Filaretti, is there something? So there is a question here. What was the most important challenge you had to cope with? From my side, and then maybe Elaine can also add, the first very important and challenging issue was the clarification of the decision that has to be assessed. I mean, it's very important from in the first place to have a very precise decision that should be assessed, and this demands to spend much time with the public authorities. Then the second challenge for me was the connection between the specific decision to be assessed and the potential impact and the models that should be developed in order to assess them. And the third one, I would say that it is the availability and variation between the different type of data. I don't know, Eleni, if you would also like to add something on that?
I agree with you, Katerina, for at least for the implementation point of view, connecting the data and actually finding the correct data in order to support the measures, because we could include other data, but they wouldn't be directly related to the measure we want to assess. So we should have data that support the stakeholders to make the decision, but also they should be able to monitor the implementation of the measure after it was done. So having enough data to support both the decision and the monitoring of the process was very challenging, and this was what we had to focus on.
Okay, thank you, Eleni. We have a second question. With regard to data heterogeneity, how did you handle that? Did you develop some data model?
Well, in the framework of CUTLER project, there was a data model that was developed in terms of environmental parameters in order to homogenize all the data. For example, we had different values for temperature, and we should make sure that they are all represented the same way, we had to conform to the spatial reference systems and the time reference systems, the units of measure. There was a model developed for that, and it is included in more of the deliverables of Work Package 3.
Yes, exactly. This was done in collaboration with the University of Oulu in Finland, and there is a relevant deliverable in the list of the deliverables. So thank you, Eleni. So I think that we have finalized our discussion today here. So once again, I would like to thank you. We are here in case you need any further discussion regarding this very important issue. Thank you very much.
Thank you very much. Thank you for your attention.
Bye-bye.